We've combined our gas laws together in one way based on our before and after set of equations. We can combine them together in a different way based on our proportionality equations. The ideal gas law is not going to be a before and after type of equation. It's just going to be one set of circumstances, where if we know 3 of the variables, we can solve for the 4th one. We've talked about Amonton's law, which says pressure and temperature are directly proportional. We've talked about Charles's law, which says volume and temperature are directly proportional. We've talked about Boyle's law, which says pressure and volume are inversely proportional. And we've talked about Avogadro's law, which says volume and moles are directly proportional. We could write those as equality equations with a c, a constant, and combine these together by looking at which side of the equal sign things are on. Before we do that, we want to rearrange Boyle's law so that everything is in the numerator. We multiply both sides by v, and we get PV equals our constant c. Now that everything is in the numerator, we can compare them and see which things are on which side of the equal sign. Pressure is on the left side of the equal sign in Amonton's and Boyle's law, so it's on the left side in the ideal gas law. Charles's law, the rearranged Boyle's law, and Avogadro's law all have volume on the left, so volume goes on the left in the ideal gas law. N, number of moles, is on the right in Avogadro's law, so it's on the right in our ideal gas law. Temperature is on the right in Amonton's and Charles's law, so it ends up on the right in the ideal gas law. We also have a constant, which I've generally been labeling C for constant, and that's on the right side of each equal sign. So that also ends up in our ideal gas law on the right side. We just changed the way it's represented. Typically in the ideal gas law, the constant is represented with a capital R, so R is the ideal gas law constant. We end up with the ideal gas law, which is PV equals nRT. I've heard a parody of the Beatles song, Let It Be, that can help you memorize this equation. nRT, 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 pressure times the volume, nRT. The ideal gas law constant is going to depend on which units we use for pressure and volume. Remember, moles is always moles, and temperature is always Kelvin in our gas laws, but the pressure and volume could be some different units. Here are a couple typical values for R. If we're using liters for our volume and atmospheres for our pressure, then we can use the value 0.08206, and the unit for R would be liters atmospheres per mole Kelvin. We have these units because they're the units needed to cancel out the other units in the equation. Another common unit for R has liters kilopascals per mole Kelvin. So if the volume's in liters and the pressure's in kilopascals, we could use the value of 8.314. Here's an example using the ideal gas law. We're trying to replace gasoline with methane. 1 gallon of gasoline could be replaced with 655 grams of methane. We want to find how much volume the methane would take up at 25 degrees Celsius and 745 torr. And we're given the value for R. You do not need to memorize the value for R. It will be given in the problem. We're using our ideal gas law, PV equals nRT. But before we can do it, we need to get things into units that we're able to use. Pressure is given to us in torr, but the value for R given to us on this slide is the one with atmospheres. So we need to get pressure from torr into atmospheres. We use the relationship that 1 atmosphere is equal to 760 torr. As I mentioned earlier in the chapter, this is going to be a very important conversion to be able to use. Since we're starting with torr, torr goes on the bottom, and 760 is along with it. We do 745 divided by 760, which gives us 0.9803 atmospheres. Now we have our pressure in a unit that matches up with our R units. N is number of moles. We're given grams of methane, so we need to get grams of methane into moles of methane. We do that by dividing by the molar mass of methane, which is 16.043. Again, if it's not given in the problem, you have to figure it out from the periodic table. 655 divided by 16.043 gives us 40.8278 moles of methane. The temperature given in the problem is in Celsius, but we need it to be in Kelvin. So we take 25 degrees Celsius and add 273.15, which gives us 298.15 Kelvin. Now we have all of the units that we need, but before plugging into our equation, we're going to rearrange the ideal gas law to solve for volume. To get volume by itself, we divide both sides by P. Our rearranged equation is volume equals nRT divided by P. Now we can plug in our values. We plug in our number of moles, which is 40.8278. We plug in the value for R, 0.08206 liters atmospheres per mole Kelvin. We plug in our temperature, which is 298.15 Kelvin. And then on the bottom, we have our 0.9803 atmospheres of pressure. When we do that calculation, we get 1,019 liters. This is equivalent to 269 gallons. We don't generally use methane in our cars because it would take up so much volume compared to just the 1 gallon of gasoline. Some vehicles do actually use compressed methane, which is often called compressed natural gas. They're using it because it burns a lot cleaner than gasoline, but it has to be compressed in order for it to fit in the vehicle. How many moles of gas occupy 15.2 liters at 27 degrees Celsius and 147 kilopascals? R equals 8.314 liters kilopascals per mole Kelvin. Is it A, 1.12 moles, B, 0.895 moles, C, 9.95 moles, or D, 90.7 moles? The correct answer is B, 0.895 moles. Pay attention to units. Temperature is given in Celsius but needs to be expressed in Kelvin before using the ideal gas law. Pressure is given in kilopascals. Notice that we are using a different value for R in this problem, which corresponds to units of liters kilopascals per mole Kelvin. Since this R uses kilopascals, we can leave pressure in kilopascals. We rearrange the ideal gas law to solve for N and to get N equals PV divided by RT. We plug in all our values and get 0.895 moles. Scientists have agreed on a set of conditions called standard temperature and pressure, abbreviated STP. STP is 1 atmosphere of pressure and 0 degrees Celsius. We can take that set of conditions and find out what volume 1 mole of an ideal gas at STP would take up. To do that, we're using the ideal gas law, but we're rearranging it to solve for volume. The rearranged form of the equation is volume equals nRT divided by P. We can plug in our values. Since we're trying to find the amount for 1 mole, then 1 mole is our N. We're going to use the 0.08206 liters atmospheres per mole Kelvin as our R. 0 degrees Celsius is 273.15 Kelvin, so we'll plug in 273.15 for T. 1 atmosphere of pressure goes on the bottom of the equation. When we do the calculation, we get 22.4 liters. That is the amount of space that 1 mole of an ideal gas at STP would take up, and we call that the standard molar volume. It doesn't really matter what type of gas we're talking about. It could be helium, it could be ammonia, it could be oxygen. As long as we have 1 mole, that is 6.022 times 10 to the 23rd molecules or atoms, it's going to take up 22.4 liters of space. The balloon on the left contains 4 grams of helium, which is 1 mole of helium, so it takes up 22.4 liters. The balloon in the middle contains 15 grams of ammonia, which is 1 mole of ammonia, so it takes up 22.4 liters. The balloon on the right contains 32 grams of the oxygen molecule, which is 1 mole of the oxygen molecule, so it also takes up 22.4 liters. As long as the problem mentions that the reaction is at STP, or if it mentions that the pressure is 1 atmosphere and the temperature is 0 degrees Celsius, or equivalent values in other units, we can use standard molar volume as a conversion factor to go between volume and moles. We can convert between volume and moles of gas at STP because we know that 22.4 liters is equal to 1 mole. For example, if the problem says at STP, how many moles is 3.75 liters of oxygen gas, we know that we can use that 22.4 liters as a conversion factor. Remember, anytime we use a conversion factor, we start with the number we're given, which in this case is going to be 3.75 liters of oxygen. That's what we're trying to convert away from. Our conversion factor needs to have liters on the bottom to cancel out with the liters we're starting with. And we're trying to find moles, so that goes on the top. Our relationship is that 22.4 liters is equal to 1 mole at STP. We do 3.75 divided by 22.4, which gives us 0.167 moles of oxygen.